Okay, so today's topic is basically, well, I guess there are two topics. One is motion capture specifically for the face, okay? And so all the stuff we talked about so far has been talking about a body with a kinematic model, and we're going to talk a little bit about how they capture people's faces, and that's a little bit different than what we've talked about so far, and it does bleed into the next chapter a little bit. So I'll kind of go over that briefly, but we'll kind of come back to some of the same ideas in Chapter 8. And the other thing is markerless motion capture. What can you do when you don't put someone in the bodysuit, right? So is there a way to estimate the articulated 3D skeleton just from somebody wearing the kind of street clothes that we're all wearing today, right? So we'll talk about, some of the challenges involved with that. Okay, so let's start with facial motion capture, okay? And so, facial motion capture is kind of a special case of the general thing. So if we had asked in the motion capture lab when we were there, I'm sure they would have been able to show us, much smaller motion capture markers than the ones that we put on the body that would be made specifically for someone's face. So for example, the motion capture markers for face are probably only going to be, I would say, a few millimeters wide. Do you know if you have any of those in the lab? Have you ever seen them? Okay, so again, it's probably one of these things where you have to pay $500 to get the marker set, so maybe you don't actually have them. But this is the kind of situation, again, where you have some array of tinier markers, and you, again, observe the person from multiple angles. You can do this with the same kind of infrared retroreflective markers that we talked about for regular motion capture, although it's also more common for facial motion capture for these to just be basically either black dots or colored dots. So one of the earliest facial motion capture systems use basically just like colored stickers like you get from the toy store to put on someone's face and watch how those things moved, and using that to drive a kind of face mesh model. It's also more common these days for something like this. This is from Tron Legacy, where Jeff Bridges was wearing this helmet that had 4 cameras attached to the bottom of it looking up at his face from below, and he was wearing this pattern of black dots that you can see kind of extends. It's not quite the same pattern as this, but it extends over his whole face, and then those facial motion markers were used to help drive the performance of this fully CG character, right? And so let me talk a little bit about that. So one thing is that unlike for regular kind of body motion capture, when you do facial motion capture, it's less common that you are going to do this kind of kinematic model for the face. Like, when you're talking about swinging your shoulders and elbows around, you have this notion of joints and bones, right? You don't have that kind of thing in your face. What you have more likely are things like muscles. And so if you look at the face literature, you're going to see a lot of talk about something called FACS, which stands for Facial Action Coding System. And the way that a facial expression is described is kind of in the sense of a bunch of these, what I would call primitive muscle motions, things like left eyebrow raised, or nose squished, stuff like that. I'm not a face expert, so I don't know exactly what the taxonomy is, but there is a list of these basic things that you can do with your face, and then if you're doing like facial recognition analysis, for example, you combine different settings of these little features to form expressions like happiness or sadness or disgust or something like that. So it's definitely more often that you'll see a face decomposed into these kind of independent, what they would call action units of muscles. Okay, although some people have like tried to develop this like super advanced biomechanical model for all the muscles and bones in your face, but that's definitely a lot less common. And so, like I said, what you have in a lot of Hollywood productions these days, like Tron Legacy and Avatar and so on, is this performer kind of carrying around a little mobile motion capture studio with cameras and markers on their face, and then hopefully, since the cameras are all kind of rigidly mounted to this helmet the person is wearing, you can triangulate to get 3D positions of the markers, and you can go from that into your facial animation rig. In practice, that is more complicated than it looks. One of the reasons being that you can't like bolt the cameras onto the performer's skull in such a way that they're totally rigidly mounted, right? So as you walk around, the rig is bouncing a little bit. The markers maybe get rubbed off as the actor, touches their face, stuff like that. So managing and cleaning up facial markers is definitely an issue for these kinds of pipelines. One thing that is actually more common and kind of relates to what we're going to talk about in Chapter 8 is this system. This is called the MOVA contour system for facial, I wouldn't call it motion capture as such, but basically, facial modeling, right? So what you see here is, the same, the same actor here, but now he's wearing what looks like green modeled makeup, right? And so what they do is they put this makeup on, and the makeup is basically invisible to the human eye. So for example, the actress on the left here is wearing this weird green makeup, but the only time you see it looking green is when it's exposed to a certain frequency of light, fluorescent light. And so what happens is they have a stage. I don't think I have a picture of the stage here. This is not the stage, but basically they have a stage full of cameras and lights, and what's happening is that the lights are flickering back and forth between white light and this fluorescent light under which the makeup kind of phosphoresces green. And so the idea is that normally your skin, right, is a pretty smooth surface, right? There's not a lot of feature points on your face to pick up on and use to triangulate. And so instead what they do is they use this kind of weird makeup pattern to provide enough texture for a dense correspondence algorithm to work. And so if you see this weird texture from multiple angles, you can kind of do this multi-view stereo problem that we're going to talk about in the next chapter. And so let me see if I've still got my video queued up for how that works. So here what you're seeing is the live performance, the captured surface with this weird makeup, and then the right-hand image is basically a 3D textured model that is not actually, a real person. That's a rendered video where they've projected the texture onto the mesh, right? And so, let me just play that again. Right, so the left is live performance, the right is the texture that they've captured kind of projected onto the mesh that they've estimated from looking at how this mesh moves. And so we're going to talk about kind of how does this multi-view stereo problem work, not next week, but the week after that. I don't know if I have a good picture of what the MOVA Capture Studio looks like. I should have, let's just see if I can find a picture of that. So I'm pretty sure that it's in this video somewhere. Right, so here what you can kind of see is that this guy is saying, conventional motion capture cameras is like what we saw. Here you can see behind him there's this whole array of lots of cameras, right, that are being used to capture the performer from all these angles, as well as lights that are, I think this is a light, I could be wrong, maybe this is just a strut. So there are different lights that are going on and off at high speed. And if I can find the picture, here you can see they're putting the makeup on. And the advantage of this is that the makeup is totally invisible under normal lighting circumstances. And so the idea is that you could light the set just as you would for a movie, not have to worry about what the performer's face looks like, and then you toggle the lighting with the weird phosphorescence. I don't know if they actually show the I think they just show the actress here not doing anything for some reason. You can kind of see in the lower corner that the lights are strobing on and off fast enough that you don't actually perceive them as ever being off. But in fact, there are these intermediate frames where you're getting this fluorescent light that's phosphorescing the makeup, and that's being collected on and off frame by a different kind of camera, right? So it's a pretty slick approach. And so, like I said, it's definitely less common to use literal markers, if you're looking for really accurate facial stuff. I mean, another thing you could do, if you had like super duper high resolution cameras, you could like literally zoom in and use your facial pores as tracking markers, right? Because if you zoomed into your face large enough, you would probably be disgusted, but you would see a lot of like little dots that are your pores, and you could imagine that something like a blob-based detector, like a difference of Gaussian or Laplacian Gaussian, would pick up those points as viable feature markers, right? So that's kind of an interesting approach too. Okay, so another option is to basically capture this person. This is, again, kind of a similar idea. This is the light stage at USC. This is a really unique facility. This is another example of an academic research lab, although now it's really used very often by Hollywood. So this is at USC. This is Paul Debevec's stuff. And so basically they will put actors in this big ball with lots of lights and lots of cameras, and by toggling the lights on and off at different angles and capturing that person from all the angles, they can basically build a model of what will this person's head look like from any conceivable angle and lighting condition, right? So typically when a production starts, they will take somebody, they'll put them in this big sphere, and they'll build this super detailed head model that they can use for digital doubles. And so, for example, this, I think that probably, actually now I don't know whether, I think this must be the actual Alfred Molina, and this one is the CG Alfred Molina. So I mean, at some point you can't really tell the difference between the picture of the person and the rendered version of the person when they projected this onto the mesh. And so, like the very last shot of, well, not the last shot, but the last time you see Doc Ock in Spider-Man 2, where he's floating down through the water after his reactor has exploded, that is an entirely CG Alfred Molina, because obviously they didn't submerge him and then sync the camera, right? So, you know, that you would never guess was not the actual actor. It looks so good. And here's an example from the Avengers, again, where, you know, they've taken the actor and the CG model. And so, you know, these days it really does raise the question of how do you know whether you're actually seeing the actor or whether you're seeing this digital double, right? I mean, this kind of thing started, you know, Spider-Man 2 was quite a while ago, and I think that also the second Matrix movie had a lot of this facial replacement stuff, like all of the multiple Mr. Smiths, right? Agent Smiths, sorry. I'm losing my cred. So, you know, and also the part where Neo is doing the thing around the pole, right, has a lot of facial replacement stuff. And so, again, we'll talk a lot about the problem of, okay, if you're seeing the same thing from lots of different camera perspectives, how do you use that to generate a 3D model? That's really a problem that I would call multi-view stereo. And so we're going to talk about that in Chapter 8, probably 3 lectures from now, okay? Okay, but that's the general idea. So, like I said, I guess going back to my boring paper and pencil, I would say that facial motion capture, you know, there are many options. There are basically, you know, 2 to 5 millimeter standard markers would be the way that you would do it with a normal kind of Vicon-based system. You could use this MOVA contour system, which is kind of like this, let's see if I can spell this right the first time, phosphorescent makeup. Or, you know, something like the light stage. And I would say that both of these things are related to what I would call multi-view stereo. As well as structured light. So structured light is another thing we're going to talk about next week, where again, you can get the 3D, you know, the 3D shape of something by basically running a specially constructed pattern of light across the surface and seeing how it deforms. That's a very common way of estimating 3D structure, and they use it a lot for facial scanning. And so we'll show some examples of that next week. Okay, so any questions about face? Okay, so the next question is, what can you do when you don't have the bodysuit? Right, so I would call this markerless motion capture. And so again, this is a, you know, broadly construed, this is a huge problem in computer vision that people have talked about for a long time, right? So the idea being, you know, I have a video, fundamentally, and I want to find the people in the video, right? So in that way, people have been talking about person detection and tracking for, you know, many, many years in computer vision. So where I want to kind of draw the line here is we want to have a system that will basically look at a video and process it into this articulated skeleton, right? So if we imagine that that is the goal, because that's the same thing that we want to do with regular motion capture, is get the articulated skeleton, because that's what we usually need for helping out with animation rigs later on, right? And so that means that we can't just use like standard person tracker, right? So for example, the kind of person trackers that you're working on, where you're just trying to find a bounding box around the person, that's not really going to help us to be able to do things like find the skeleton of the person, right? So we need something that is going to be better than that. And so the kind of key idea is that we need a model for, you know, what I would call skeleton, which I would call theta, and how that turns into an image, and let me just call that R. Okay? So basically, the idea is that if I tell you, okay, here's a skeleton, and I know where the camera is, what should that person's body look like from this angle? So that means that we kind of have to put flesh on the skeleton, right? So basically what we need to do is, you know, turn this into a solid body model, and then we kind of compare these two things to say, okay, so if I were to see this fleshy skeleton from one angle, I compare it to the picture I actually see of the person, and I try and modify my skeleton until I bring those two things into as well of an alignment as possible, right? And I'll show some examples of this in just a second. So, big picture, let me just say that, you know, markerless motion capture is definitely not as good as regular motion capture. And there are a lot of reasons for that. You know, one reason is that, first of all, images are just really ambiguous compared to markers, right? So if you look at this example, so the first problem you have to deal with actually in a real system is finding the person in the image, right? So that means that we have to do a really good job of segmenting the person out of the image, which is again like a chapter 2 kind of matting problem, right? So here you can imagine that if I was trying to estimate, this is a pose of me somewhere in Alaska, so if you wanted to estimate my pose from this image, well, you know, first you have to separate me from the background, and that's a non-trivial natural image matting problem, right? So the best case scenario for markerless motion capture is capturing someone in front of a green screen where, again, you can subtract out the background relatively easily, right? So that's the good situation. So let's suppose that you have me in front of a green screen and you got this picture in B that is just me in my street clothes, right? So now you think about this and you think, boy, you know, this is going to be a tricky image to estimate my skeleton from for a variety of reasons, right? So for example, you know, you can't really see what my right arm below the elbow is doing, right? So there's really no way to resolve like this twist of my wrist or anything about what my right hand might be doing. And even my left arm is kind of tricky because, like, if you think about my elbow, it's probably like here, and so my left arm is really foreshortened, right? So I mean, again, there's very little information about what my arm below my elbow might be doing. Similarly, like, look at this. You know, this is a bulge of fabric around my knee just from the way my pants are hanging, right? And so if you're trying to think about where would you find my knee in this picture, it's pretty tricky, right? I mean, you know, it's nothing like the situation in the motion capture lab where you have these very precisely placed markers close to the skin that really define the position of a joint, right? You don't have anything like that when you just have an image, right? And so you can imagine that already the problem is much, much harder, right? And in fact, I think it's been estimated that from a typical image, you really only see, like, at most 2/3 of the possible joints that you would need to build the whole model. And so typically what you have are a bunch of cameras that see the person from a bunch of different angles to resolve all these missing data points and ambiguities. And so another thing to kind of keep in mind is that, you know, this is just a still image, but as I'm moving, right, even if I were to say, okay, well, this point on the pants corresponds as well as possible to my knee, you know, the problem is that my clothing is baggier than a skin-tight suit, right? And so, you know, as I flex myself, all my, you know, external clothes are going to change in a non-trivial and probably non-predictable way with what my joints are doing underneath, right? And so that's really challenging, right? Remember in the motion capture lab, we were told that socks were bad, right? And socks, when you think about it, socks are probably the most closest fitting item of clothing that you're probably wearing, right? So, I mean, if socks are bad, imagine how bad, you know, jeans or, you know, a sweater would be, right? And of course, you know, that's also assuming that you can still even perceive, you know, all the joints. I mean, if you have a woman wearing a skirt, right, then you've lost a lot of the bottom, you know, half of the body due to things that you can't even see, right? And so, you know, definitely a much harder problem. Okay, so I'm going to talk about in a second, like, how we try and solve this estimation problem. I mean, all that being said, you can still get some pretty nice results with the caveat that it's never going to be as good as a markered system. And so probably I think a good rule of thumb is that at the time that I wrote the book, you know, even if you were to look at, like, people will compare, their markerless systems to markered systems and then see how far off their predictions were. And, the markered systems are still taken as ground truth. And so we can find kind of sub-millimeter accuracy for markered systems, whereas, markerless systems are probably more on the order of like centimeter accuracy for joints. I mean, again, getting better, but a lot of that accuracy is just inevitably compromised by the nature of the clothing, right? I mean, it's not like a high resolution camera will necessarily help you with some of these problems. You're just kind of stuck by the fact that, you just can't estimate those joints very well. Okay, so let me talk about kind of the model that we use, right? So the idea is that, what I have is a series of images over time, and what I want to estimate are the corresponding series of joint angles, right? So again, these are like the images, and these are like the kinematic models. And without going into a lot of detail, basically, the way we typically try and solve this problem is we want to maximize the probability of a given set of joint angles given these observations. Okay? And so this is what I would call a dynamical system. Well, I guess I haven't gotten to the dynamical system yet, but this is basically what we want to do. It's kind of like a Bayesian problem. And so we, when we talk about Bayes' rule in probability, right, the way we can solve Bayes kinds of problems is by flipping around what we, how we relate the observables to the unobservables. And so what we need something like this. What's the probability of seeing these images given these joint angles? Okay. In some sense, that's an easier problem because I assume that I can go from a joint angle candidate to a crude picture of what that person should look like. It's kind of like I put the flesh on the skeleton and I kind of make a model for what that image should look like. And again, typically we model this as, the product of each of these things, right? So it's like saying that, the images at successive times only depend on the joint angles at that point in time, right? There's not like this higher dimensional time coupling, right? So we kind of separate out and say that we assume that, the image I see at time t only depends on the skeleton at time t. That stands to reason. And we also need a kind of dynamical model. The probability that I see theta of t given these previous joint angles, right? So that's like saying, instead of having to make an instantaneous decision every time about what the joint angles are, we have a model for where I can be at time t based on where I've been before, right? And so, again, if I really wanted to, I could bring in, physics, and I could bring in, acceleration and velocity and so on. A lot of times, you make this into a very simple Markov model, which is just saying that where I am at time t, I have a probability, like a transition probability between where I was before and where I am now, right? And so, you have a kind of, you can imagine that I could model this using some sort of a, it would be a bad idea. You could model this as some sort of like high-dimensional Gaussian, just say, okay, the joint angles at time t, I expect to be pretty close to the joint angles at time t minus 1, because, things can't move that fast. And conversely, even if I do move, I know that there are certain directions of motion that are more likely than other directions of motion, right? So, again, I don't want to get into the details exactly of how you, I will talk about this guy a little bit. How do you estimate the probability of seeing a certain image given a set of joint angles? I want to talk about that next. This, basically, comes from, could come from physical model or training data, right? So remember we talked about last time, if you're doing the inverse kinematics and you want to estimate, what's the probability that the body is in a certain state? Well, you know things about how human bodies move by collecting lots of data, right? So you could have some sort of a model for that. And then let me just say that the variables involved here are all fairly high dimensional, right? So I mean, a joint angle, right? Again, so if you think about a joint, I think that one of the problems in the homework is to estimate how many degrees of freedom there are in the little sketch of the kinematic model of the body that's in the figure in the book, right? And so the number is probably like in the 40s or 50s, right? So you've got this very high dimensional model, and unfortunately, it's hard to work with things in such high dimensions. And so typically what we use is something like a particle filtering approach, where you kind of have a set of particles that represent possible hypotheses, and these allow you to do things that are more advanced than just like a simple Gaussian model. I see some puzzlement.
So when you mentioned like high dimensional stuff, I
right.
immediately go down to something like PCA.
Yes. So PCA is also a possibility. Yeah, for sure. Yeah. So another thing you could do is, instead of using an agnostic particle filter, you could say, okay, I'm going to observe lots of models for how people move, and I'm going to boil down this 50-dimensional joint vector to a 6-dimensional vector of human motion. Right. So that's also a very viable. Yeah. So that's a totally viable approach. Yeah. Okay. So the main question, I think, for this kind of topic is, this guy. So how do I, given a skeleton, how do I predict what the image should look like? Okay, and so fundamentally, well, there are a couple ways to do it. I mean, if you were a kind of, if you had this amazing computer graphics model of a person, well, then in theory you can pose that person however you want and render the image and compare it to the image that you have on the day, right? Now, you're probably not going to have this amazing 3-dimensional model that not only includes the person's body shape, but also whatever clothing they happen to be wearing on that day, right? So typically what we do is make it a little bit of an easier problem, right? So typically what we do is we often, sounds like they're pressure washing the hallway or something. We often simplify the image using either silhouettes or edges. And so what I mean is the following. So here, I've got this guy walking, and what I'm going to do is I'm going to, instead of trying to estimate a lot about this image, all I'm going to do is try and estimate the foreground of the image, right? Which is the kind of same thing I would get after I had done a matte. I would get the foreground, right? So if I think about white as person and black as not person, you get these pictures, right? And so the silhouette, gives me some information about the body shape without me having to worry too much about, color and texture inside the body. Now, one problem with the silhouette is that it can be kind of ambiguous, right? So actually, if you look carefully at this picture, you can see that all of the people in the top row have different poses, right? So one of them is kind of in a walk cycle that is like this. Another one is like in a walk cycle like this. And if you think about the frontal or the side view of that person, they both produce almost exactly the same silhouette. Or, if I think about my arm out like this, or my arm out towards the blackboard, then again, there's a lot of degrees of freedom that you actually can't see just from the silhouette. So that what the implication is that you have to gather a lot of silhouettes to disambiguate these issues. So if I saw the person from 4 or 5 angles, well then maybe I could get silhouettes that would make more sense, right? So if I saw the person from the front, in this case, I would be able to kind of disambiguate all 3 of these. Well, I'd certainly be able to disambiguate, this case from this case. And if I saw the person like kind of from the top, I could probably disambiguate these 2 cases, right? Another thing is that if I allow myself to also look at edges, right? So I mean, again, if I have the silhouette and my arm is crossed in front of my body, if I just think about the silhouette by itself, I lose everything about this left-hand arm here. Whereas if I also say, okay, I look at the edges of the foreground, then you can start to perceive the arm inside the body. And so kind of the name of the game is that what I have on the top is kind of like the image of, captured from my camera. And I say, okay, here's the person, here's the silhouette, and here's the edge map extracted from the real image. And the bottom is my model that I say, okay, if I've got my skeleton, I can pose my kind of 3D stick figure, and then I can look at what would be the corresponding silhouette of that and the corresponding edge map of that. And then the way that I try and optimize my cost function is to try and make the silhouettes and the edges from all the cameras match up as well as possible, right? So that's a very simple way of doing markerless motion capture. And so let me kind of be a little bit more specific. So what I can do is I can say the goal is to try to bring the silhouette and edge maps from the model, or from the image, into agreement with the model as much as possible. Right? So kind of the way I think about this is, okay, what I want to do is I could say, okay, the probability of observing this image given my theta is kind of proportional to, e to the minus something. And this something is kind of like saying, okay, I have some weight on the, this is the number of cameras. I say, what is the distance between the silhouette from camera I at time t and the predicted silhouette from camera I at time t, right? And this is just like saying I need to have, these two binary images, I need to compare them, right? And so one thing that would be easy is just to say, okay, I'm just going to look at the number of white pixels in those images that agree, right? So when the overlap is good, thinking about, this picture, when the overlap between these two guys is good, then most of the white pixels should be the same, and most of the black pixels should be the same, right? So you kind of think of a very simple kind of binary metric between those two things. And so then I could also, I guess I could add a weight here, and then I could have another weight that says, okay, I could also look at the distance between the edge map from camera I and the predicted edge map from camera I. And again, in that case, what I have is, kind of looking at the comparison between two line drawings like this. And so in this case, you have to be a little bit careful about the edges in the sense of saying, okay, well, there may be a lot of edges in the image that are not in the model, right? Because, for example, if I'm wearing a striped shirt, I'm going to have a lot of edges inside my torso that don't appear in the model unless I also have the model wearing a striped shirt, right? So what I want to say is basically that every edge in the model should appear in the image, but not vice versa, right? So, if there are strong edges in here that don't appear in the actual image that I have, well, then probably that's not the right pose, is the kind of way to think about it, right? So you kind of think about what is the right way to design these cost functions. And there are some details about, exactly how would you, go about designing each of these little bits of cost functions, but that's the idea. So then what I want to do is that when this distance is small and this distance is small, then e to that distance is, as close to 1, or it's 1, right, or as close to 1 as I'm going to get. And that means the probability of seeing that image given the pose is high, right? We want to maximize that is what it comes down to. So that's kind of the idea, is, very high level of how you could start to build this kind of markerless system. So in some sense, all of this stuff is operating entirely in the image space, right? So I've got M cameras looking at the person, and I am only comparing the images of the person to the images of the 3D model, right? Another thing that you could do is you could, okay, so before I move on, any questions about this? Okay, so another thing that I could do is say, okay, well, really what I'm trying to estimate is a 3D thing, right? I'm trying to estimate the 3D position of the body. And so what I could do instead is to say, okay, well, let's think about it. if I were to take the image that I saw and I were to project it out into 3D space, then basically, you know, I know that the 3D voxels occupied by that person have to be within this green boundary, right? Because they project onto that silhouette in the image, right? So you can imagine that if I kind of intersect these cones of pixels for multiple cameras, what I can do is I can kind of carve out the possible region of 3D space where that person could be, right? And then I try and fit my model inside that 3D space, right? So this is kind of a clever idea. So this is kind of what I would call the visual hull, is what it's called. So let me just back up and say that, you know, for all this stuff to work, including the silhouettes and the images, you need to have calibrated your system. You need to have calibrated your cameras, right? Because otherwise you don't know how to match up the pose of the person in your model to the image that you saw, right? So unfortunately, you can never get around camera calibration. You still have to do something that is analogous to waving that motion capture around, the motion capture calibration wand around my cameras to obtain the 3D positions of all of them. And again, we talked about that a few chapters ago about how if I were to just take my checkerboard, I could wave it around my world of cameras and use that to get their 3D positions, right? But you have to for sure do something like that. So in this case, what I'm saying is, okay, I see this, you know, 2D silhouette, and I project out into the world this 3D thing. And then I could say, okay, well, if I intersect all those things, I have what's called the visual hull, okay? Now, how would I do that? Well, I guess that picture was about as good as I can get, but let me just say, you know, what I would say is we can talk about visual hulls. I can basically, I guess I have actually a picture here, like this. So I can basically back project the occupied region of the silhouette from every camera view, and then that produces a possible set of 3D voxels in the 3D space where the object is constrained to be, okay? Now, the object definitely could be smaller than that. I mean, in some sense, all I know is that the object surface has to be kind of tangent to the edges of this 3D volume when viewed from each of the appropriate positions, right? But, you know, there are lots, you know, there's a lot of ambiguity about what that shape could be given that constraint. And that's where the human, you know, 3D model comes in, where you actually know this is a head and a torso and shoulders and legs and stuff like that, right? Now, how would this kind of come together mathematically? So basically the idea is that I back project silhouettes into 3D space to get, you know, kind of possible voxels that can be part of 3D skeleton. And then I can kind of add a term that says, okay, you know, the probability of observing the image from the model is kind of proportional to some sort of a distance between the visual hull that I get from my so this is basically the observed visual hull, and this is the, you know, voxels from the 3D model, right? And so it's kind of like saying, okay, you know, you voxels that you generate from my model have to fit inside this 3D space that is generated by projecting the silhouettes forward, right? And so that basically, you know, is a more, well, that's really going to get you further than just using the silhouettes and the images alone. And you could kind of combine this plus silhouettes and edges to do even better. You know, one kind of caveat is that, let me just note, I don't know what that is, note, quantizing the 3D space can be costly. or if you do it badly, that means that your 3D reconstructions are inevitably a little bit blocky, right? So I mean, if you think about, suppose I want to take a picture of me and model the voxels I take up in 3D space. Well, I mean, if you were to take like, say, 5mm cube voxels, there would be like many of them, and it would be very computationally difficult to keep track of all those voxels all at once, right? So when you see these voxel carving and visual health techniques, usually what you end up with are fairly kind of blocky 3D, models. And so here's an example of that. So what I did is I took a bunch of pictures like this. And so again, since I don't have the high quality, studio when I was writing the book, what I did was I made a little turntable with a little mannequin on it. And so this thing, just as a side note, is my little calibration object, right? So we talked about how do I calibrate the camera. Again, what I did was, since I didn't have a lot of calibrated cameras all at once, and I'm rotating this thing, what I did was I said, okay, I'm going to assign some known 3D coordinates to each of these corners on this colored set of cubes, right? So if I said, okay, then this corner is 0, 0, 0, this corner is 1, 0, 0, this corner is 2, 0, 0. So basically what I did is I built a 3D coordinate system from the corners of these blocks, and then I knew I could basically apply a resectioning algorithm that said, okay, I know the known 3D points, I can click on where I saw them in the images, and then I use those to calibrate every one of my cameras. And so that was a little, homebrew technique for calibrating cameras. Once I know that, then I can look at a bunch of, images of this mannequin from different perspectives, and then I can carve the voxels and get something that is a crude, human representation, right? Now, this is okay from the left-hand angle, not so great from the right-hand angle, so let me just show you, in MATLAB, what the corresponding voxel carving looks like. You could argue about it. So, I mean, definitely humanoid, but, you can also see that from other angles, not so great, right? So here's a question from the top, right? There's this big thing sticking out of the mannequin's chest, or I guess there are two big things. And part of the issue is that, fundamentally, all of those voxels, like you think about seeing it this way, so this is like seeing a person from above with their arms stretched out like this, these weird chest sticking out pixels are consistent with all of the views that I happen to take, right? And so I would need to take some more pictures to rule out all those voxels. And so, for example, if I just took a picture from the top, right, I would probably carve away all the stuff that I, didn't like. The other thing is that, here, this is purely voxel carving. Like, I haven't actually tried to fit a 3D kinematic model to this, right? So now, you can imagine that if I have a model of my mannequin, then what I would be doing is kind of like I'd be trying to pose the mannequin in my 3D model to match up as well as possible with this 3D set of voxels. You can imagine that might work decently well if I had a good initial position of where things were, right? But clearly, more cameras are required to get a good model in the first place. And you can also see that there are some, this is kind of a quick and dirty thing. You can see that, you can almost kind of sense the way that these voxels have been kind of scraped away by the rays from the camera, right? You see these kind of weird diagonal lines. Those are kind of correspond to things that are parallel to camera rays, and that's why they look kind of like things have been kind of shaved off from different directions. So it's kind of a neat idea, though. Okay. So I can close this up. And like I said, even though this is kind of cruder than motion capture, with markers by a long shot, you can still do some cool stuff with it. And so, for example, there was a scene in Quantum of Solace, right, the second James Bond movie, where the second Daniel Craig James Bond movie, where they're falling out of an airplane without parachutes, I guess. And so what they did was, instead of attempting to model these two actors with like their hair and the cloth flapping around, trying to do that with a computer graphics model would be pretty complicated because it's like super high speed, right? So what they did instead was they took the actors and they put them into one of those like free fall wind tunnel things that you can go to for fun. And so they put cameras all around the periphery of this wind tunnel. They threw the actors into the wind tunnel in costume and they filmed them from a bunch of different angles with calibrated cameras. And then what they ended up with were basically 3D textured chunks of voxels that when you put them back into the image, they actually look pretty good, right? So this scene was fundamentally done with voxel carving, with visual hulls, instead of trying to make like these super accurate models. And so it turned out to look pretty good, partially because it would be very difficult, like I said, to model like cloth simulation for someone jumping out of an airplane, right? That would be really much more complicated than actually getting the actual visual data. But that being said, I'm sure there was an enormous amount of rotoscoping and matting to actually extract the foreground masks for each of these images. So there was still a lot of work involved with somebody having to outline what happens in each scene. But that was a case where they actually used something like that in real life. The other thing is that just in the same way that we talked about how you can do very accurate facial motion capture with this light stage at USC, there's also other light stages for doing body motion capture, right? So there are systems like this. This is a real image of all these lights and all these cameras in this huge hemispherical dome, and they'll put actors into this dome, and then they will be able to generate what would this person look like from any angle and any lighting condition, right? The caveat of this is that what you get at the end of the day here is you get a very, very nicely detailed 3D mesh model of the person, right? And one thing to remember is that mesh model is not always what you need for subsequent animation for your rig, right? Typically, you don't necessarily want a mesh model. What you want is the articulated skeleton, and then kind of going from that to skinning the rig to get the fleshed body. So, it's the kind of thing where, you can do some cool stuff with it, especially if the person is not moving much from the pose that you captured them in this thing. But, it's not the same as the kind of output of a motion capture system, right? So again, this is very, this is becoming more related to what we're going to talk about in the next chapter. We're talking about, this is like a huge, large-scale multi-view stereo problem where you've got, lots of images. What do you do with them, right? But you can see this must be an incredible environment to stand in, right? And so, again, even though I think this is I'm sure it was funded partially by Hollywood, but fundamentally, this is a thing that is sitting on the USC campus, right? It's not owned by Hollywood, and all the Hollywood productions come in and use it, right? So this is another example of where academia can kind of help out. The other thing is that you may be familiar with the Microsoft Kinect, right? So the Kinect, if you've ever looked at what happens under the hood, is a direct depth sensor, and from that depth sensor they obtain a skeleton that you use to drive the, let's see if I can fit the page width here. So it uses the estimated skeleton to, I don't know why I can't figure out the zoom levels. I'll just zoom in manually. So we're going to talk about this on the next two lectures, fundamentally how this works. But basically, what you get is a depth map, which is basically for every point that's observed, a distance from the camera to the person, right? So stuff that is closer will appear to be, I guess, darker in this view, and stuff that's further away will appear to be lighter. And then what they do is they trained this crazy model for, they had lots of cases of real images, and they also had lots of simulated images of people where they tried to match up, okay, given this raw depth image, roughly what are the body parts? So here you can say that purple is head, green is left leg, yellow is right leg, and then here's the corresponding skeleton. And so fundamentally, they took, literally, probably like a week on some massively parallel computer to train this classifier for, given the depth image, what is the corresponding skeleton. Then they implemented this in hardware on the Kinect, so that once you've got the model or the classifier, the real-time classification of the skeleton is extremely fast. Like, it's just a very fast decision tree that they implement frame by frame on the Kinect. So the first Kinect, I'm not sure about the second Kinect, but the first Kinect had no built-in temporal dynamics at all. It was just literally taking every depth image and spitting out a skeleton with no reference to what the skeleton was before. And so that's why if you look at the raw skeleton output from the Kinect 1, you often see that it's a little bit jumpy because there's no sort of smoothing going on. You can do the smoothing later if you want. And the other thing that these guys at Microsoft had to figure out, which was pretty impressive, was that you have to think about the typical glamorous actors that you see in motion capture suits for Hollywood are not like the typical people that you see playing games at home, right? So you have to deal with a huge variety of body shapes and weird perspectives and stuff like that. And so getting it to work well for basically anybody that stands in front of the Kinect was a huge engineering, thing. So very impressive. The other thing to keep in mind is that the goal of the Kinect is not like highly precise, skeletal estimation. And so if you were to actually drill down and look at how accurate is a skeleton, you know, it certainly, I don't think, could compete at all with a mocap system. But for understanding, you know, how you're controlling a video game, it's certainly more than good enough, right? So it's certainly good enough to distinguish punches and kicks and swipes and stuff like that. And so, you know, again, that was like this massive effort to train this classifier. So we'll talk a little bit more about the Kinect next time. The new Kinect is not based on the same technology that the old Kinect was. And so we're going to kind of talk about both of those technologies in the kind of direct 3D sensing stuff. Okay, so that's more or less what I want to say about motion capture. Any questions about stuff? All right, so in that case, let me shut my system down here.